some questions on order type. So it's kind of nice that Xavier is the next speaker, follows right after Esther and Mihály. In fact, I think that the first time I heard of him was when he found beautiful solutions to problems related to line transversals of balls. So there was this line of research that was pushed by Miha, the geometric permutations, and in fact it also stems, of course, in the work of Ricky and Eli, Hadwiger type theorems. But at any rate, I am very happy that Xavier accepted our invitation and will give another talk related to order types.
Yes, so thank you very much. And thank you very much for this occasion to speak. I think I consider I owe really a lot to Ricky and Eli for helping building such a nice community, welcoming. And I especially felt that they were really welcoming themselves. So I'd like to talk about some questions on order types. And so as János mentioned, order type is something that they really got into when they started working together, coming out of their respective areas of expertise. And Eli walked about this in a recent issue of DCG, basically explaining that they wanted to work together, that is version, and they look for the simplest question that they could ask. What is the simplest geometric object? And perhaps one way to present this is assume that you take a sequence of reals. They're wise distinct, so because we're going to talk about points, let's consider these to be points on the real line. And you only have access to one information, which is given 2 points. You can ask whether one is left or right of the other. Of course, when you know that for any pair of points, what you know is the order of the points, the permutation that they define, right? And you could even play the game of identifying all those configurations that you see, these orders up to relabeling. And of course, then you get something completely trivial. You get only one equivalence class. Not much interesting things is happening. And perhaps the surprise is that if you actually do exactly the same thing in dimension 2, then you get a very rich and very intricate structure. And these are what the order types are. So this is something that Ricky and Eli introduced in a paper that's entitled Multidimensional Sorting. And basically the only question you need to decide is, what do you mean exactly by comparing 2 points? So here in the plane, we're going to compare 3 points. And we will have a predicate, the orientation predicate, that takes an ordered triple of points, ABC, and will output 1 if they turn left, -1 if they turn right, and 0 if they are aligned. And of course, to keep things simple, let's forget about the 0. And once you have this, if you follow this line that we started in 1D, you're going to look at 2 sequences of points, the P's and the Q's, and you're going to identify them, or to at least declare that they have the same labeled order type. If anytime you take 3 points from the P's and you look at their orientation, you would get the same answer looking at the orientation from the Q's with the same indices, right? So in a sense, if your only length is orientation, the P's and the Q's, they are the same to you. And this is what this definition capture. It's reducing the diversity of the point set to a finite number of type. And of course, if you now start looking at examples, you can look at the examples on 4 points. You will get these 8 different configurations, these 8 different labeled order types. And it's natural to see essentially 2 families. They're right, the 4 points are in convex position, or they are not. And this, of course, is what you end up with if you identify up to relabeling. Okay, and in that case, you end up with what's called order types, which are simply the equivalence classes of point sets up to having a bijection that preserves orientation. Okay, so an order type is just an equivalence class of point set that are equal up to bijection preserving orientation. And so what I would just like to do now in the 20 minutes or so that are coming is just go through a few natural questions that arise regarding this combinatorial structure and highlight some of the contributions that Eli and Ricky made. They have very beautiful theorems, and I'd like to share my enjoyment of some of them, and also mention some recent development, a few are a bit less recent, that shows that what started there is really pretty much alive, okay, and very active. Okay, so the first question, these are combinatorial structure, how many are there, right? And this is a question that they settled at first order in that paper, which was already in DCG. And so they first proved the lower bound. Let me go through the lower bound first. It wasn't actually stated as a theorem, right? In their paper, it was just stated as a remark. And what the remark was that you get n to the 4n up to some noise. This is a big noise, actually, right? Because it's an exponential multiplicative term in n, but compared to n to the 4n, it's actually noise. And the way they prove this, it's very elementary. You start with 2 points, and there's only one way to place your 2 points. And now your 2 points, they divide the plane if you take the lines through them. And if you place the point number 3 on one side of the line, it doesn't matter where you place it. So there's only one order type of size 3 that you will get, labeled order type of size 3 that you will get by placing the point 3 on this side. And of course, there's another one that you get on the other side. And so you multiply by 2. You started with a single configuration, or you get 2. And you start doing this again. You draw all the lines through pairs of points that divide the plane into region. And every time you pick a region and you place a point there, you will get a different labeled order type on 4 points. And it doesn't matter where you place your points in that region, you will get the same one. Okay, so you multiply by 7 and you keep going. When you add the points one by one, and when you add the point number n plus 1, you pick a cell in the arrangement of all those n choose 2 lines for 2 points, and you get roughly order n to the 4 cells to choose. And that means that the number of labeled order type is going to grow like n to the 4 times n minus 1 to the 4, etc. That's n to the 4 factorial. Okay. And again, this is ignoring constant factors that get multiplied n times. So this is ignoring exponential factors. So things became much more interesting going for the upper bound. And the upper bound, as Andreas mentioned before already, and what you do is you actually map your endpoint sets to points. So you move to a configuration space where one point in your configuration space is an n tuple of points. Okay, so you're in dimension 2n. And there, second idea is to realize that, as Micha mentioned, the orientation is a sign of a polynomial. Okay, and now that means that all you have to do is take the sequence of all those polynomials, you get n choose 3 of them, and look at the signs that can be realized in your 2 endpoint sets. And one way to do that, to deal with these kind of problems, is to bound this from above by the number of connected components that you end up when you basically cut off the space by removing the 0 set of all those polynomials. Okay, every time you move a point within a connected component that of this complement, then the signs remain positive or they remain negative, they cannot vanish. Okay, so your orientation remains the same, so your combinatorial structure remains the same. And of course, now that you map your problem to this counting the number of connected components, you can use bounds from real algebraic geometry that were already mentioned quite a number of times. Okay, and as I understand, this is why Ricky got into real algebraic geometry, And let me also contribute to showing this beautiful picture of this book. I think it's a feature that has been shown in all the talks. It's a really, really, really nice book with Saougata Basu and Marie-Françoise Roy. So, and interestingly, the bound that you get here is also n to the 4n, again with some exponential noise. And let me share just some surprise with you, because in a sense, what they're doing with their lower bound is they're extending point sequences. So you're starting with a sequence of points, and you're adding points, and that's kind of building a tree of point sequences that you extend. When you have 3 points, you get 7 descendant, and so on. This one gets 7 descendant, and it continues. And if you've played around a little bit with order types and point sequences, then you're probably familiar with the idea that if you want to reach all the realization, all the extensions of an order type, you cannot start from a single realization. Okay, from a single realization, you will get, when you add a point, you will get to n to the 4 extensions of your order type, but there could be actually much more extensions that exist. And this is related to the allowable sequences that Andreas Olsen talked about in the first talk. It's actually, if you want to know what are the possible extensions, you need to know what is the arrangement of the lines that goes through pairs of points. So it's much finer than the order type. And to have a measure of how much can we miss here? If you take points in convex position, then naturally inside you will get order n to the 4 region if you draw all the chords through 2 points in the circle. And it turns out that the number of order types of endpoints with exactly 1 point inside is exponential, or close to being exponential. This is a recent result by Peels, Welzel, and Wettstein. And so that means that you're actually missing most of them when you're picking a single realization here. And so in these 3 arguments, it could be that we're missing a lot of the branching here, if what we are really interested in is counting order types. But interestingly, the Goodman and Pollack bound, it's the first order is the same for the lower and upper bound. So in a sense, it doesn't matter too much if you look overall in average. And this is something that could perhaps be interesting to elucidate. It's are these convex configuration the only ones that have such a discrepancy, or is this something that we could grasp? This might help perhaps to refine the bound that we currently have. Okay, moving on. A second very natural question is, how much precision do you need when you want to visualize order types? So because we're forbidding line triples, that means that whenever we have a realization, a point set that realizes an order type, we can actually perturb it slightly. And if the perturbation is small enough, we will still have the same order type. That means that you can always find realization with rational coordinates. And that means with appropriate scaling, you can always get realization with integer coordinates. And so the question is, how big have those integers to be? And a very nice result by Ricky and Eli and Bernd Sturmfels, and part of it was also found by Krastovil and Matocek, is that a regular grid of size doubly exponential in n, first it suffices, but it is also sometimes necessary. So if you actually want to represent your point set with integer coordinates, you will need an exponential number of bits to write them down. And the proof is really beautiful. It uses ideas from von Stott's algebra, where he actually realizes the operation of algebra via projective geometry. So that goes back to the 19th century. Let me walk you through it, because if you've never seen it, it's really breathtaking. So you start with, you walk in the plane, and you start with the real line with a point that is distinguished as 0, and then any point represents a real that is a distance to 0, right? So you get x, you get y, as you're familiar with. And so how can we construct the sum of x plus y, or how can we construct the product of x times y? Well, for the sum, you take a parallel to your real line, and you take any red line, and you mark the point, the blue point, and you draw the parallel to the red line through y. And now from the blue point here, you draw the line going to x, and you draw its parallel. And of course, it will get to x plus y. Okay, and if you're getting a new chance because now I'm going through the product. If you want the product, well, you do the same. You draw any line through 1. You hit a certain point. You draw the parallel to this line through y, and of course, you now draw the line from this point to x, and you draw the parallel. And Thales tells you you've reached x times y. And this can be projectivized, so you don't really need to use parallels. You could just distinguish a line at infinity. So you distinguish a point here, you draw a line there, and you use it instead of parallel. So whenever you need parallels, you take lines that actually intersect on this line at infinity. And you can do the sum, and you can do the product in the same way. Okay, so this is what von Staudt came out with. And this is what Ricky and Eli and Bernd Stromfels did, how they use it. So they started with this projective configuration with 0, 1, and some x written here. You can think of x as being the number 2. And they use this construction to build the number x squared. And you again build the construction, use the construction to build the number x to the 4. It's actually very far to the left. And you keep going. You apply this construction to build x to the 8, and you keep going n times, and you end up with x to the 2 to the n. And along the way, you've built a linear number of points, okay? And those points, they have many alignments, many incidences, the incident structure is very constrained. And it is actually so constrained that if you just forget the points and you just take the incidence constraint and the alignment constraint, any realization you can come up with will be projectively equivalent to this one. And that means that the ratio of the smallest distance to the diameter, you will capture it through just a single one of those realizations, because it will be recast as a projective invariant. Okay, it will be some harmonic ratio. It will show up there as some harmonic ratio. And this seems to be very peculiar to having many alignments and many concurrences, but this construction can be perturbed to get a generic order type, a simple order type with no line triple, and where any realization will have to be very close to being projectively equivalent. Okay. And along this line of research, there have actually been many work coming up recently. So one natural question is, okay, there are some order types that require exponential precision for being drawn, but how many do? And actually, we are getting more and more examples of large families of order types that can actually be drawn on polynomial size grid. And as you can see, the latest bound by Schöscher is already at first order of the right magnitude. So it could still be an exponential factor, an exponentially small fraction of all order types, but we're getting there. You can also study the typical grid on which you could round a random point set and still keep the order type structure. And you can use that to actually analyze the typical patterns that you see in an order type. Okay, and there are more examples that are known of specific order types where we can actually control the space of realization, or at least control the space of realization of certain subsets of the order type. And of course, this is polling some very deep water with very problematic results that tells us that, you know, only so much can be done, because there is this beautiful result of Nyoff that tells you that actually a realization spaces of order type, they can be arbitrarily complicated. And this can be formalized as, if you give me any simplicial complex, there exists a labeled order type whose space of realization will have the same homotopy type as your complex. So it can have, not only is it not connected, can actually have arbitrarily many connected components. Okay, and they can have arbitrarily many holes of arbitrary high dimension, because actually this is not only a two-dimensional complex as I drew, but it's an arbitrary finite simplicial complex. Okay, so these are actually monsters, but some of them are pretty nice and friendly, and we are getting to know them a bit more. And the third problem that I wanted to tackle is actually random sampling. And there's actually some papers that mention the Goodman-Pollack model of random point set. I'd actually take some tracing down to find out what this actually is. I'll come back to that later. But a very natural question is, how can you generate a random labeled order type or random order type in a way that is pretty diverse and pretty efficient? And there are two different natural approaches to that. One is because we just saw that certain order types you cannot draw without devoting exponentially many bits to represent the coordinates. Maybe you want to stick with combinatorial structure. So the only thing you need to record is for every triple, does it go left or does it go right? But of course, if you do that, so one thing is, out of all these possible maps, very few will be order type, will encode labeled order types. Okay, only exponential 2 to the n log n out of the 2 to the n cube will be objects you're interested in. And actually, the worst news is if I give you one such map, it's actually NP hard, or actually existential theory of the real hard to decide whether it encodes an order type or not. So dealing with random order types from a symbolic point of view, it doesn't work so well. So of course, there's a natural thing that we all do whenever we want to test a conjecture on random point set, whether it depends only on the order type or not. We just take a random point set and read off its order type, right? And of course, this begs the question, what probability distribution should you consider? And actually, does it matter? If you take points uniformly in a disk, in a square, from a Gaussian distribution, whatever probability distribution in the plane you like, and you sample independently and uniformly, what effect does it have on the probability distribution that it will induce on the combinatorial structure? Is there a way to relate these two things? So one way to think about that is to actually look at the shadow of this probability distribution. So there's this area that is interested in random geometric objects, stochastic geometry. And one of the very fundamental problems that was started by Sylvester and was very much developed in the second half of the 20th century is the study of random polytopes. And a typical model of random polytope is that you take probability distribution, uniform in a disk, square, whatever, and you sample endpoints there, and you take the convexal. And that is your random variable taking values in the space of polytopes. And people have been studying this model a lot, and we know a lot of things about that. In particular, we know the typical distribution of the number of extreme points. And here I'm simplifying a lot the results, much more precise on that. But if you're looking at points uniformly in a disk, what you will get is then to the 1/3 extreme points on average. If you take points in a square, you get much fewer. You get only order log n. And if you take points from a Gaussian distribution, you get even fewer. You get only order root of log n. So this already tells you that this should be quite different in terms of order types, because the number of extreme points that you can read from the order type. So which one of those distribution is better? Well, perhaps what you can do is do the same thing, but for random order types that you choose with equiprobability. So the uniform distribution on the combinatorial objects. What is this typical number of extreme points? So if you look for 4 points, well, you get the average between 4 and 3. You get 3.5. If you go for 5 points, you get the average between 5, 4, and 3. You get 4, and so on. And it turns out that this average number goes to 4 as n goes to infinity. So you typically only get up to 4 points on the convex hull. So this is something that we could prove recently with Emo Welser. Hello, Emo. And this actually shows you a lot of that. These three results, when you confront these averages here with this average and you add a little bit of concentration bound, it shows you that the order types that you get from this distribution of point set, they are very concentrated, meaning as n goes to infinity, there will be subsets of order types that will represent a vanishingly small fraction of the order type that you will hit with probability going to 1. So you will keep looking under the proverbial lamplight. Okay. And now coming back to this probability distribution that Ricky and Eli coined, it's actually very nice. Their idea was to take the regular simplex in n dimensions, so you get n plus 1 point, apply a random rotation to that, and project it to 2 dimensions, and you get a random point set in the plane. How good could it be? Unfortunately, it's actually very close in distribution to the Gaussian distribution. So this one also, if you're reading your order type from that, is concentrating. So if you want to learn more about this, there is a very beautiful survey on random polytops by Matthias Reisner. So that's where I recommend to get started. So there are many more questions that we could go through. Rick and Pollack introduced this idea of lambda matrix to encode efficiently order types. It's n square log n bits. There were recently some subquadratic encoding for order types and for labeled order types. There's some work in geometric Ramsey theory, the beautiful same type lemma that was revivified with the semi-algebraic hypergraph and which improved quantitatively on this original same type lemma. You can think about forbidden patterns. I think there are very nice problems there, but let me stop here. I am seeing some question in the chat. Yes, I should have mentioned. So order types are a subset of uniform acyclic oriented matrices of certain ranks. It's not exactly the same in the sense that you could you can think of order types of point set as a combinatorial type of the duals of arrangement of lines, and acyclic uniform oriented matrices are the combinatorial type of arrangement of pseudo lines. So they are more general. There are many more of them. Particular order types are realizable by definition, David. Yes, that's what I meant. Otherwise, they are often called abstract. Realizable acyclic uniform chirotops of rank 3 if you're working in the plane. I believe that's correspondence if you want to be careful.